Hi everyone, am I audible?
Yes, sir.
Okay, so let us start with this week's problems. Okay, so we have been given a circuit here, and what we have to find the pole in the transfer function. So find the pole, we first need to find the transfer function itself. So let us see how we can do that. This simple question. So in this is grounded. So I will take this as virtual ground, and I will apply KCL here. So if I take KCL here, I will get V in minus 0 by R1 parallel 1 by SC1 uh, equals to 0 minus V out divided by R2 parallel 1 by SC2. Okay, I'm just equating current through this branch equals to current through this branch. And okay, so what is, let's calculate one. R1 parallel 1 by SC1 equals to R1 into 1 by SC1 divided by R1 plus 1 by SC1 equals to R1 by SC1 divided by R1 SC1 plus 1 SC1. This and this cancel, so we get R1 by R1 SC1 plus 1. So we will put that here. V in by R1 1 plus SC1 R1 equals to minus V out by similarly R2 1 plus SC2 R2. Okay, so V out by V in equals to minus R2 by R1 1 plus SC1 R1 by 1 plus SC2 R2. So this is our transfer function. Okay, so to find the pole, we need to equate denominator to 0. So when we do that, 1 plus SC2 R2 equals to 0. So S equals to minus 1 by, this is the pole. So we know C2 is 8.3 picofarad and R2 is 1.3 kilo ohm. 8.3 picofarad, R2 equals to 1.3 kilo ohm. So what you should get is, so you should get pole S equals to minus 92.68. So any doubts in this part? Okay. So next is what's the location of 0 in the transfer function. So this is very similar and easy. We know. So what is 0? 0 will be the, when we equate this equal to 0, we will get 0. So numerator term 1 plus SC1 R1 to 0 is equals to minus 1 by C1 R1. And this you will get as 32.95. So this was also straightforward. I will go to the next question. Okay. So in this question, what do we have to find? What is the output impedance? The window source. So we have to see from here and find the impedance Z out. Okay. So let us find that out. And what is given? Okay. Let's see. Let me draw this. Okay. So this circuit is given. This is an NMOS, and we have to find Z out seen from here. So as we usually do to find Z out, let us apply some voltage here V, and let the current flowing through here is I. Okay. So so in the question given is that we can disregard RL in our calculation. So we'll only assume like there's no current flowing through here RL, no I mean no AC current flowing through here, and since this is an op amp, an ideal op amp, the current going through here I will also be zero. So the only current I will be equal to is I is equals to minus ID. Okay. So okay. Now let us see. So when you have applied this voltage V here, so the gain, let the gain of this op amp be A. So when V voltage is applied here, so in the non-inverting terminal, so this is an op amp minus plus. If I apply V here, it is grounded, so output will be minus AV, right? This is minus. So the output here will be minus AV. Okay. So we know now the voltage at this terminal, and this terminal. So now we can find ID. We'll apply the small signal equation. ID equals to GM VGS plus GD VDS. So GM, what will be VGS? VGS, the gate voltage minus AV, and at sources minus V. So here gate is minus AV and source is minus V plus AC0 and source is V. So it will be minus V. Okay. So I will get, let's take V common. Let's take minus V common. GM A plus 1 plus 1 plus GD to ID. And we know this is equals to minus I. Minus minus cancel. So V by I equals to 1 upon GM A plus 1 plus GD. Or if you want, you can replace GD by 1 by R naught. So you will get R naught divided by 1 plus GM R naught A plus 1. Okay, this is Z out. This is Z out. So is there any doubt in this part? Till here, is there any doubt?
Sir, repeat how we got the minus AV as the output of the op amp.
Sorry, what did we get? V as output.
See, the output of the op amp is given as minus AV, right? Please explain me
Oh,
again,
okay,
sir.
okay. Yeah, yeah, yeah. Okay, sure, sure. So let me draw here again. So let us see, this is an op-amp. Okay, this is inverting terminal, this is non-inverting terminal, and then apply voltage V here. So this case is same as this case, right? This is, I have an, in at the inverting terminal, I have just applied V, and here I have not applied anything. So this is same as this. Can you like appreciate this, that both these conditions are same?
Yes, sir. Yes, sir.
Okay. So simply for an open loop configuration, the output of an, if A is the gain, then the output is A times V plus minus V minus. So V plus is 0, it will be A times 0 minus V minus AV. Uh, do you understand now?
Sir, what about the virtual short concept here? Uh,
Okay, so yeah, virtual short concept is only applied in feedback, not in open loop configuration. Okay.
okay. Okay. Oh, understood, sir. Understood.
Okay. So
Sir, this is in
if
feedback, right? Negative feedback.
this is a negative transistor. Like what if there was negative feedback, I would have applied the V in at here, not at here, right? I'm directly applying a voltage V at this node. So it is just like an open configuration, not actually feedback.
Okay, got it.
Are you saying something?
I got it. Yeah.
Okay. So anyway, so this is the Z out that we get. And one more thing is, okay, yeah. Let's see one thing. Okay, so to find that, I think all the things given, K is given, lambda is given. Okay, so GM equals to 2 under root KID, and we know GD equals to lambda ID. K is given, lambda is given. What will be ID? ID will be input V in by RL. V in by RL equals to 1.2 by 43, 27.9 something milliampere. Okay, so one more thing that I want to tell is, when we are talking about virtual short, so we are short, we short these two. So what we are doing is that we are making a DC short there, right? So it means like currently this I'm talking about are the small signal voltage. These are the perturbations that are here. If we apply the virtual ground concept, if there is some DC bias here, let's say it is 1 volt here, then I can say, yeah, it is 1 volt here also. But on that 1 volt, I am applying some small AC signal. That will not, like, so am I able to explain this? Like this is a small signal, not the biasing. That is why, like, I've not taken VV00 here. Okay, so should we move ahead in the next part, or do you want to ask something here?
Sir, is there any way to consider the equivalent of the op amp itself, like MOSFET?
Sorry, can you repeat?
See, for MOSFET, we have the equivalent, right? The GM uh, um, VGS like that. Similarly, so if there is any equivalent for the op amp, and we can put it directly there, and we can analyze that. Is there any way that?
Uh, yes, you can, but I think you can make an equivalent circuit for op amp also. So, but it requires many parameters, like let me see. So if
Okay.
you make an op amp, so there's something called Zn. If this is, let's say, V plus and V minus, then you will have A times V plus minus V minus, and there will be some Z out also. So this can be an equivalent for the op amp, but in general, we do not know all these parameters, right? So for an ideal op amp, what we do is plus minus. We only know these two, V plus V minus, and we have to find this output. So what we assume is this gain is very high, and this impedance also is very high. So that is why we just apply virtual short and solve it.
Okay, sir.
So this is actually easier just by drawing the symbol and the analysis. It just for solving any op amp question, you just need to apply KCL at any node that you see. So you may gain more confidence and you solve more similar questions. Let's see. So this question is similar to the previous one. It's just this op amp is flipped, minus is above and plus is bottom, and this is a PMOS. So let us solve this. Again, so I'll apply some V here and let the current I flow through here, and current through this is ID. So for PMOS, this is drain, this is source, this is gate, right? So now again, if this V is here, the output here will be, this time it will be plus AV, because I am applying to the positive terminal, I am applying V, so output will be plus AV. Okay, so now let us write the equation ID equals to GM VSG plus GD VSD for PMOS, right? So GM VSG, source is V minus AV. Oh, okay, sorry, I written it wrong. Nobody corrected me. This was, so this is drain for PMOS. So GM it will be minus AV plus GD minus V. Minus I equals to V AGM plus GD V by I 1 by AGM plus GD ZM. Are you losing me somewhere in this? I think. Should I repeat this?
No need, sir. Correct, right? Getting so.
Okay. So the only thing that you need to do is if you are so whenever we want to find Z out at any node, we just apply a test voltage and we pass a test current through it, and just then V by I is Z out. So I wanted to find Z out at this node. I just applied a voltage V here and a current I. That we how that we will propagate here is that it will become plus AV through this op amp. That's it. Okay. So now, okay, yeah. So this is a sine wave oscillator. Okay. So the total capacitance is 24 picofarad. That means 2C equals to 24 and C is 12 picofarad. What is the value of R such that circuit oscillates at 1 megahertz? Okay. So let us see. So let us assume something. So let's say the V voltage here is V1, the voltage here is V2, and this is just an, so this is R and R. So output here will be VO equal to minus R by R into V2, right? That is minus V2. So output here will be minus V2. Is this clear why it is minus V2?
Because inverting side.
Yeah, because it is just simply an inverting amplifier with both R and R. So if you know for any, okay, let me just tell. I'm not sure if you guys know. I'll just show. This is minus, this is plus. Let's say this is feedback resistor. This is R1. Let's say this is V1. This is, my screen is not shared. Sorry. So consider this op amp. So RF is the feedback resistor. R1 is the input resistor. Okay, let me call this as V1 as V minus because I am applying at inverting terminal, and this let me call as V plus. So the output V out is given as minus RF by R1 into V plus plus 1 plus RF by R1 to V minus. Sorry, written V minus V plus. So have you seen this before?
Seen, sir.
Yeah. Okay. So this is the same
I
thing
have seen,
like,
sir.
yeah. So if you have not, please let me know. I'll tell from where this comes from. It is just simple KCL. So when you apply KCL at this node, you can get this output, and we assume here we assume virtual short and we assume V plus here. Okay. So back to the question. So this is, if this is V2, this will be minus V2. Okay. So let us apply KCL at this node first. So with that, okay. Before that, let us apply here in this node. So here it is V2, here it is V1. So one is current flowing through here, that is minus V2 by R, and one current is flowing through here, that is minus V1 by SC1. Okay, V1 by 1 by SC. Okay. So if we write KCL at this node, minus V2 by R plus equal to minus V1 by SC, 1 by SC. This will give V2 equals to RSC V1. Right. Now I will apply KCL at, let's say, which node? This node. So here current will be V1 by R, and this current is minus V2 by 1 by SC. So at this node, minus, okay, not minus, V1 by R equals to minus V2 by 1 by SC. This implies V1 equals to minus RSC V2. So what I'll do is I'll put this value of V2 in this. So I'll get V1 equal to minus R square S square C square V1. V1 and V1 cancel. So let me write here. 1 equals to minus R square S square C square. So 1 plus S square C square R square equals to 0. Okay. So what we have to find here is okay, the oscillating frequency is 1 megahertz and R, okay, fine. So if you like compare it with the equation for second order systems, if you remember 1 plus 2 zeta by omega n s plus square by omega n square equals to 0. So let me write it in the next page. So, one point. Okay, so this is something that you might have studied in some control system course. So this is the characteristic equation for any second order system. So where zeta is the damping factor and omega n is the natural or oscillating frequency. So if we compare these, we first thing we can see is zeta will be 0. That is the damping is 0. And why, if we see from this circuit why it is 0. So the damping will come from if there is any resistor in parallel with any of these capacitors. But since there is no resistor, we will always have this term as 0. If there was any resistor here, here or here, then we would have plus 1 s, some let's say a times s term. So the zeta would not have been 0. So anyways, so if we compare this and this, what we get, s squared c square r square is equals to s square by omega n square. S square cancel, so omega n square equal to 1 by r square c square omega n equal to 1 by rc. And so fn equal to 1 by 2 pi rc. C is given, r is given, oh, r we have to find, and fn is also given. Fn is how much? 1 megahertz. And we can find r to be 13.26 kilo ohms. Okay. Any doubts here?
No, sir.
Okay. Please let me know if you lose me somewhere. I'll repeat the things again. So question 6, okay, question 6, 7 and 8 I'll come at last because they are a bit confusing. Let us first solve 9 and 10 quickly. So, okay. Yeah. So what we have to find is CMRR. So we have seen it before also, and it is CMRR equals to AD by AC. Okay. So let us find AD and AC, then we can find CMRR. So this is a circuit. Let this be, let me write it as V1, let's say this is V2, let VO1 and VO2. Then by for an ideal op amp, this by virtual short, this node will also be V1, and for this node will be V2. Okay. So if we write uh, VO1, what will VO1 be? VO1 equals to minus, okay, let me just first again write the equation for an ideal op amp. Vout equals to minus RF by R1 into V1 plus 1 plus RF by R1 to V plus, let me write it as V minus plus. So VO1 will be, what is RF is RB minus RB by R1 is RA, and here voltage is V1 at the inverted terminal, V1 plus 1 plus RB by RA into V plus is also V1 only. Have I done? Okay, sorry. I've done something wrong. This will be V2. This will be V1. Yeah. So if you see here is this V2 will be the voltage at the non-inverting terminal. So it will be V2 and this will be V1 at the non-inverting terminal. V2 is the at inverting terminal. This equation is clear, or should I repeat? Like I got a bit confused earlier. So should I repeat this equation? Uh, are you following, guys?
Yes, sir. No, sir. Not
Okay.
not required.
Okay. So similarly, we can write VO2 equals to minus RB by RA into V1 plus 1 plus RB by RA into V2. Okay. So now let us just do, let me call it 1 and 2. If I do 1 minus 2, then I will get VO1 minus VO2 equals to 1 minus 2 V1 minus V2 RB by RA plus V1 minus V2 1 plus RB by RA. So it will just give me VO1 minus VO2 by V1 minus V2. It is actually AD. It will be 1 plus 2 RB by RA. Okay. Now we will do the similar analysis for ACM. For that, let us apply VCM here, and let output be VO1 and VO2. VO1 equals to minus RB by RA. Okay, so this will also be VCM. This will also be VCM. VCM plus 1 plus B by RA VCM. Similarly, VO2 will be minus RB by RA VCM plus 1 plus RB by RA VCM. Okay. So if you see, these will cancel. This is minus, this is plus, similarly here and here also. So if we write VO1 plus VO2, if we add these two equations, we will just get 2 VCM. VO1 plus VO2 by 2 VCM is to 1. This is ACM. Then CMRR AD by ACM equals to 1 plus 2 RB by RA by 1 equals to 1 plus 2 RB by RA. So this will be your CMRR. Okay, so you have to just put values of RB and RA and you have to find it in dB. Okay, so make sure you calculate that correctly. So answer will be here 28.29 dB. Okay. So let us see this question now quickly. Then we will go to others. So here we have to find the input impedance seen from here. So let us solve this. So I will redraw it. I'll rotate and draw minus plus, and plus side is R1. Which R is this? R1. Minus side it is R2 and R2, and here it is R3. So and this is grounded. We have to see Z in from here. This is the outlet. So again, yeah. So these two circuits are same now. So again, we will apply test V here and let current through it be I. So no current will go here. It is an ideal op amp. The I current will go here. Okay. So what do we do is let us first apply KCL here only to find the V out here. So if we apply KCL here, we get V by R3. Okay. 0 minus V by R3 to 0 here and V here to virtual ground equals to V minus V out by R2. So minus V R2 by R3 equals to V minus V out. V out equals to V1 plus R2 by R3. And okay, so what is I here? So this I is voltage here minus voltage here divided by R1. So I equals to V minus V out by R1. V minus VR2 by R3 divided by R1. V and V cancel. So I equals to minus V R2 by R3 R1 plus V by I equals to R3 minus R3 R1 by R2. So this is the Z out here. And all these values are given, and you should get answer as minus 23.72 kilo ohm.
Z in, sir. Notations.
Sorry, yeah. So Z in. Okay. Now coming back to one of the questions we left earlier. Okay, so was there any doubt in this question? Sorry, I forgot to ask. Should we move ahead?
Yes, sir.
Yeah. Yeah.
Will input impedance negative?
Yeah, it is negative.
Okay, sir.
Okay. So this question is a bit confusing, so I'll try to clarify what they want to ask. So they are saying that op-amp is to be designed for gain of -2. Okay. So if we take uh, how do we get -2 gain is, say we take some R here, so minus plus another R here, let's say R1, R2 ground, and we apply some V in. So output is -2 V in. So that is 2 is V out equals to minus RF, sorry, minus R2 by R1 V in. So R2 by R1 equals to 2. Okay, so they want to design something like this, but and they're saying the error that they can tolerate in this gain is this 0.04%. Then what is the maximum gain of the op-amp that you require? So this is the gain of the circuit, but what is the internal gain of the op-amp to enable this? So ideally we were considering this internal gain to be infinity, but now we cannot consider. So if when that was infinity, then only we could have considered this as virtual short, and then how we were solving it. But now they are saying that it is finite. So let's say that gain is k. So let me try to solve it. Well, it all plus minus. Let me draw it bigger. So, um, and this is connected here. And here we are applying V. This is ground plus minus VID. So so when the gain is let's say this gain is not infinity, so we will draw this kind of circuit, let's say. So are you getting like how I have drawn this circuit?
Yes, sir.
So next is nothing. We will just try to solve this. So we know VO is K times VID. And what is VID? VID is here it is 0, and here it is, let's say, V1. 0 minus V1. So VO equals to K 0 minus. So what will be V1? So V1 will be V in R1 by R1 plus R2 if we apply the superposition theorem, plus VO R2. Okay, let it know VO R2 V in R1 by R1 plus R2. Is this clear how I have replaced V1? So let me tell again. So here it is VO, here it is V in, here it is V1. So this is R2, this is R1. So I will apply superposition theorem. I'll first consider one of them as 0. Let us say this one is 0. Then V1 equals to V in R2 by R1 plus R2. Then I will consider this one as 0. Then V1 equals to VO R1 by R1 plus R2. Then I'll just add both of them. Then V1 equals to V in R2 by R1 plus R2 plus VO R1 by R1 plus R2. Okay, so that is how I am replacing V1 here. Yeah, okay. So mm, let me do something else. So yeah. So VO equals to K minus K V in. Let me take this R2 and divide it by here R2. So what I will get by R1 by R2 plus 1 plus VO, and I'll do the same here, 1 plus R2 by R1. So I'll get something like this, right? Okay. So so when we were doing this, so if we see the our gain V out equals to minus A V in. So this is our gain. So A is what? R2 by R1. I'll replace this A there as R2 by R1 equals to minus K V in by 1 by A plus 1 plus VU by 1 plus A. Okay. So VO minus K A times V in by 1 plus A plus VO by 1 plus A. Okay. So let us add a page. I'll copy this equation. Is everything clear till this step? What have I done? What is A? What is K? Is it clear? Let me write K is the uh, open circuit gain of op amp. A is the R2 by R1 gain of feedback circuit. Can anyone please confirm that you are getting what I'm telling you? Else I'll repeat.
Yes, sir. Gain of inverting side.
Yeah. Okay. So we are till here. So now we will try to just solve this equation. So let us take VO at one side. So 1 plus K by 1 plus A plus 2 uh, V minus K, v, K A by 1 plus A V in. So VO by V in is
A,
yeah,
that is 2.
1 plus A divided by. Okay, what one thing that I can do here is let me
Q by
take
V by
L
A.
1 plus A plus K divided by 1 plus A equals to minus K by 1 plus A V in. So cancel this. VO equals to VO by V in equals to minus KA 1 plus A plus K. Right. So if I take this k in denominator, so I will get minus a upon 1 plus a by k. Okay. So why I am like trying to bring it in this form, because this is now the gain of the circuit, right? And we want that gain of circuit to be simply just minus a, minus R2 by R1. But once we have considered this k as non, if this k was infinity, right? Then k tends to infinity, gain tends to minus a. That is what we want. But k is not infinity now. So k has some value. So instead of getting just minus a, we are getting this additional error term. So this is what the question has been asking you. So if this error is 0.04,
2%.
yeah, sorry, 2%.
That is this year, sir. Sorry, sir.
Okay. Okay. So this is what the question has been asking you. If that error is given, find out what should be the k. So now we know what is error. So let me just copy it here again. Okay. So let me write this. This term is error. Okay. So E equals to 1 plus A by K. So what should be we know this is 2. This is 0.04%. So what should be K? So K is equals to 1 plus A by E. To 1 plus 2 by, if you write percentage, 0.00004. I think 1 0 is extra. Let's check. 04. So we will get as 7500. So this should be the minimum gain of the open loop amplifier. And in dB, it will be 77.5 dB. 20 log 7500 equals to this. So this is the answer. So it was a bit confusing. So is it clear?
Yes, sir.
Okay. So in the next question is pretty much straightforward. So in the next question, they are just saying they have now an input offset. So what they're saying is that in an op-amp minus plus, if let us say R1, R2, and we get some Vout. So this difference is VID, right? They're saying this VID is already 1.6 millivolt. So it is like I am applying 1.6 millivolt here. Then what is the output? That is the extra output, that because this 1.6 is already present even when I'm not applying anything. So what is that extra output? So it is simply VO equals to 1 plus R2 by R1 into 1.6 into 1 plus 3, sorry, 1 plus 2 into 1.6 equal to 3 into 1.6 equals to 4.8 millivolt. So 4.8 is the answer here. And the last question also, let's see quickly. Okay. So they're saying that op-amp transfer function is of the form this, where A is the DC gain that you computed earlier. So they're calling what is A. Let me write. A is the gain that we computed, and gain will be computed earlier was minus A by 1 plus A by K. This was the gain that we had computed earlier, right? So let me just, they're replacing it by A. So let me take some other notation here. This is G. Okay. So calling this as A. Okay. So Okay, sorry. This is not. This was the gain. Uh, let's say VO by V in that we computed earlier. Saying this K is replaced by this. So they're saying now K is A upon 1 plus S by omega naught. Okay, so this was the internal, what considered open DC gain of uh, op-amp, and now they're saying it if we take that whole transfer function, it is represented like this. So what we will do is we will put this replace this K with this. So let me write there U by Vi equals to G upon 1 plus G by K, and I'm replacing K by A upon 1 plus S by omega naught. Right. Yeah. So minus G upon 1 plus G upon A 1 plus S by omega naught. Okay, so equals to, so this VO by V nothing but transfer function minus G upon 1 plus G by A plus S upon omega naught 1 plus G by A. Okay, so to find the oscillation frequency or the 3 dB frequency, what they will do is we need to find the pole. So for that we equate the denominator with 0. So I'll copy the denominator equals to 0. Okay. So I'm missing something. Okay, anyways, so 1 plus G by A, let's say S upon omega naught 1 plus G by A, and if we want to find omega naught equals to, can replace S by omega. So we know S equals to J omega, right? So if I write here J omega. So what I want to do to find uh, the frequency, we will equate the imaginary part and the real part. So with that we will get 1 plus G by A omega by omega naught 1 plus G by A. So omega naught equals to omega G by A divided by 1 plus G by A. So this is what you have to solve now. Okay. So we have to find omega naught. Omega is given as 14 megahertz. Okay, it is, you will need to multiply it by no, or divide it by 2 pi. On 2 pi is omega. G we know is 2. A we had calculated, A was 7500, or A or K, whatever that was earlier. That was 7500 we had calculated in previous question. So if you find omega naught, you should get 35.17 kilo radian per second. Okay. So this is how you have to solve this last part. Uh, is it clear?
Okay, sir.
Is is there any doubt in anywhere, or we can close for today then?
So what will be the noise in outcome? How it will be?
Sorry.
Will in earlier weeks we said in cascode and differential amplifiers noise will be less. We have to try to reduce the noise and interference. What will happen in the op-amp? Will there be a noise?
Okay. So how do we characterize noise? Is so op amp is simply an amplifier, right? So whatever input. Okay. If you see, let's say this question. So op amp is simply an amplifier. If noise, let's say minus plus, if noise is coming here, let's say you're applying some signal Vi, but you will are getting some noise also. So it will amplify noise also, A times Vn plus Vi. But you see what this circuit is called is an instrumentation amplifier. What it does is uh, if there is noise at both these terminals, it tries to negate that, and that is why we get ACM was low. It was ACM was just 1, and CMRR was very high. So CMRR or ACMR is how we quantify noise here. And simple op amp is not very good at suppressing that. So we use this instrumentation amplifier configuration to suppress noise. But for that, the requirement is that these two resistors should strictly be same. Does that answer your question?
Yes, sir. Okay.
Okay. Anything else? Okay. So let us close this session for today. Please let me know if you have any questions. You may email me or comment on the video. Thank you, guys.
Thank you, sir.
Thank you.